See the flash. Now it's on.
Okay, cool. Now it's on. All right. So we want to do number 49 in 18.1, which says there is a force due to gravity, which is given by this thing.
Yep.
Cool. So the force is minus the universal gravitational constant times the mass of Earth. What the hell's that R?
It's the. I'm assuming that's the distance of the object from the Earth.
From the center.
Okay, so here's Earth. Here is object,
Okay.
right? That R vector is either this one or minus that one. You guys with me on that? Which one is it? Force should be a mass times an acceleration, right? Which way is this thing going to tend to go?
Towards Earth.
Due to gravity. Forget its initial whatevers. Due to gravity, it's going to tend to go this way, right? You guys see that? Okay, so the R vector that they're talking about is this one.
Oh.
Because they slapped that minus sign on there, right? So that means it's getting pulled the other way. That's cool with that?
Okay.
And then the R norm of R cubed under there, where's that guy coming from?
That's just overall distance.
Yeah, so that's the length of this R vector, right? Which is the distance from the center of the Earth up to your object. You guys all good with that? Why is there a cube on that? I thought gravity worked as a square law. Isn't gravity an inverse square relationship?
If it's squared, then that one on top will cancel out, right? Make it square.
Perfect. Cool. So this is really, right, minus gm over the magnitude of r squared times r over magnitude of r. You guys see that? This guy's giving you the amount of force, and that guy's giving you a direction. Why do I know this guy, this r over norm r? Why does that only contain direction information?
Because that'll be a vector. That won't be a scalar.
It'll be a vector, not a scalar, but how long is that vector specifically? Yeah, that's a unit vector, right? You guys see that? Cool. So what this thing's going to do, right, is this is going to tell me how hard it's pulling in which direction, right? And now I'm supposed to do number 49, which says I want to calculate the work done by the force of gravity on a particle of mass m as it moves radially away. Oh, I'm missing something. What did I miss when I wrote this formula down?
Forgot to write down little m.
Yeah, I forgot a little m in there. I assumed mass 1 here. There should be a little m here. You guys all good with that? I just forgot something in the formula. Okay, so I'm supposed to calculate the work done as this thing moves radially from 8,000 kilometers from the center of the Earth to infinitely far away.
Yeah, that's what was kind of confusing me. I get it at one point it's going to be negligible if it's infinitely far away. I don't know like at what point that becomes negligible.
Good, cool, it doesn't ever.
So it does become negligible?
If you put two things any finite distance apart and there's nothing else in the universe, those two things will gravitationally attract one another. Is that force negligible?
Yeah, I'd say so.
I mean, at some distance, right, it's not really going to matter. You guys with me on that? That's this question that I told you guys was in that XKCD what if about the gravitational pull that all the spiders exert on me, right? Like, do I feel myself pulled towards the spiders? Not really. It's not enough to overcome friction, right? Like, I'm not being dragged slowly towards the concentration of spiders in the corner. Is there a giant egg sac in that corner, by the way?
Couple of chairs.
No giant spider with an egg sac?
No.
Cool, good.
No, that's in my house.
It was there the other day.
It probably moved. It knew you found it, so it had to hide somewhere else.
Probably it was just pulled through gravity to somewhere else, right?
Gravity falling.
Like that happened. Oh, yeah, I bet that's exactly what happened. Probably I have more friction than it does, so it was pulled towards me. It's probably in my house. Perfect. So, anyway, what the hell do I do with this?
What are you trying to
Well, I don't know what you're
assuming-
assuming. If you bound it from 8,000 infinitely away, how would you express that bound? Like, could you actually solve this?
Yeah, I think we could solve this. So, what I have is, how about this? Which direction does this happen in? They just said radially away, right?
Mhm.
What the heck does that mean? Like, here's my object. What does radially away mean?
That
The
must
opposite
mean in a
direction
straight
of
line
the
from the center, right?
Yeah, means parallel to a straight line from the center. So you're going to move that way, right?
We rocketed something out.
So that r vector is going to be,
Positive, right?
I mean, it's going to point straight to the center of the earth, right? You guys see this vector, right? The which direction is that pointing in? What's that going to be?
Unit length towards Earth.
Yeah, that's going to be unit length pointed at Earth, and I'm not changing the direction of Earth, right? You guys see that? Because we're moving radially away, that piece is going to be constant. So I may as well just assume that's like 1.
Well, you couldn't just pull that and get rid of it, right? If it's 1, you couldn't treat that as 1, you just take it out of the equation.
Yeah, not really. So when I write my equation down, right, I'm going to integrate. And I need to figure out my path, and I suspect that my bounds are going to start at 8,000 and go to infinity. You guys cool with that? Okay, and then I got like, all right, there's minus universal gravitational constant, mass of Earth, mass of my little thing, divided by,
Magnitude of our squared.
that's going to be weird, right? You guys see that? So let me maybe parameterize my path, right? What's going on in your path? It's a straight line. I'm going to do this. I'm going to just go like this. I'm going to declare some axes. You guys cool with that? So I'm going to declare these axes.
Would you want that to be R though, for working regularly?
It doesn't matter at all, right? You guys see that? Like, I'm working radially. It doesn't matter which direction that thing's in. It's always going to be exactly the same. So I'm just going to force it to be something because my brain works better that way.
Okay.
So I'm declaring this is my unit, kind of, right? My coordinate system. I'm just declaring whatever direction that is, that's going to be in the x direction. Y is going to be at right angle to that, and z is going to stick straight out of the board.
Yep.
You guys cool with that? I got to declare that because, well, it doesn't matter.
Yeah.
You guys cool with that?
Okay.
Okay, so what's my path I'm talking about then? What's my r path?
dx, or is that what you're saying?
Yeah, it's just along the x-axis, right?
Yeah. So it'd be t 0, 0.
So it'd be maybe t 0, 0. You guys cool with that? Okay. So I've got this stuff, that's over the magnitude of r of t squared. I'll fill that in a second. And then times a r of t over the magnitude of r of t. And then, so that's my vector field, right? You guys all with me on that? And then what am I dotting that with?
0, 0.
I need a dt, right? Yeah. But what goes here? So categorically, what is this whole object?
That'd be,
F of R.
Yeah, that's f, right? That's my vector field evaluated at r of t.
so then you would need
Oh,
yeah.
Yes! Good. I need an r prime, right? Categorically, this sucker's a vector. To get a scalar, I need to dot product it with a vector. So I'm going to dot product with r prime of t.
which would be 1, 0, 0, right?
Perfect. So now let's fill in our bits and bobs. Okay, so I am getting the integral from 8,000 to infinity of, oh, a lot of this crap is just constants, right? So I'm just gonna pull some of that out. Like there's a minus. What else is constant in there?
The mass and the gravitational constant is
So the universal gravitational constant is surprisingly enough
constant.
constant, right? And then there's the mass of the Earth, also constant.
The mass of the object should be constant.
Mass of the object, also constant. And then, okay, let me put in pieces now. I think I got as many constants as I'm going to get without screwing this up. So that's a 1, right? So if I could call that stuff out. What's r of t? What's the magnitude of r of t?
It's t squared.
It's t squared square root, right? So it's t, and I'm squaring it. So I get t squared there. Please note you should be worried as hell about negative signs there. Right?
Oh, right.
You guys cool with that? You need to be concerned because you just took something, squared it, and then square rooted it. You made it positive. Right? But
We squared it.
we squared it again anyway. And where am I bound? My t's are all positive, right?
Yep.
Okay, so I'm not sweating the negatives, but only because of that. Then what else you got here? You got dotted with, oh wait, that's not dotted, that's scalar multiplication, right? So what's r of t divided by t's norm? That's this thing over t, right? T comma 0 comma 0 divided by t, which is the vector 1, 0, 0, right? That's the I vector. And now I'm dotting that with, what's r prime? 1, 0, 0, also the I vector. And then I need a dt here, right? So this guy is
Just one.
I dotted with I is just 1, right? It should be a scalar. So if that thing's 1, then I think I have here minus g capital M little m, the integral from 8,000 to infinity of 1 over t squared dt. You guys all with me on that? Okay, now what?
That would be it, right? You really can't plug an infinity sign into an
Oh,
equal.
sure you can.
Oh, Meryl would die to hear you say that.
Yeah, create a limit.
Yeah, take a limit, right? I want to push that top value towards infinity, right? So I might do, okay, let me put an n in here
I think usually
and
it's
take a
substitution.
limit capital N tending to infinity. Like that would let me do this?
Yeah, we usually.
But I'm going to use shitty notation. So I'm just going to put my infinity up here. Because I trust that in spite of yourself, you've seen this and done this before.
Yeah.
Okay, so what is the antiderivative of 1 over t squared?
Negative 1 over t.
Yeah. So I got minus g capital M little m minus 1 over t evaluated from 8,000 to infinity, right? Which is minus g m little m. What's minus 1 over infinity? 0, right? In the limit, it's definitely 0. So you got 0 minus
1 over 8,000.
minus 1 over 8,000. See that? So I get also minus g m little m over 8,000.
Well, it's also 1 over 8,000, so the negatives cancel. Oh, minus would negative. Never mind. Negatives
Yeah, the
cancel.
minus wasn't a problem at first. So what's that telling me?
That that's how much force you're gonna have to give, work you're gonna have to do to get out of the universe,
Yes.
basically.
That's the total amount of work you have to do to get your object of mass little m from 8,000 kilometers from the center of the Earth to gone. Please note, this does not tell you how long that takes,
Nope.
right?
T equals infinity.
This is just the total amount of work it takes. And keep in mind that's also signed work, right? Because this vector field is what?
Negative.
Not freaking helping.
Yeah, the vector field is actively
Right.
against you.
This vector field is acting against you in this process, hence you get a negative answer, right? Because it's hindering your process of moving this thing up. You guys cool with that? Cool. Also, this is just the work done to get that object out, right? Not the work done to get any fuel part way so that you can burn it so you can do some work. You guys see that?
Also doing all of their
Also
options.
not the work that you need to do to get the fuel that you need to burn part way from the beginning. And also not the fuel that, you guys see this? This is called the tyranny of the rocket equation. This thing that, right? You need a little bit of thrust way up here, like way out at basically infinity, right? But to get that little bit of thrust, you have to bring some fuel, right? But that fuel requires a little bit of extra thrust at the previous burn, right? So you have to bring a little bit of extra fuel to push your fuel. And then at the previous burn before that, you have to have fuel to push the fuel and the extra fuel and the payload, right?
It's
So
basically
the
like
fuel
the
has-
space age version of Zeno's paradox.
Yeah, exactly. It turns out that there is a limit in there, right? That you can sit down and write this out, figure out exactly what it is based on the fuel efficiency you're getting, but it's a bear, right? This thing does cause rockets to be really annoying to work with. Cool. Which is why everybody's all ooh and awing about reactionless drive, I guess.
And why it's called rocket science.
Cool. Questions, things?